Earth Systems 3209. Unit 4, the forces within Earth. Unit 4 can be referenced in the textbook in chapters 14, 15, 16, and 19. It also can be referenced in the curriculum guide in Appendix A and Appendix B. Unit 4, Topic 4. This topic will look at evidence which supports plate tectonics, and will focus on outlining and describing current evidence which supports the theory of plate tectonics. When we look at the evidence for plate tectonics, the main evidence to support the idea of plate tectonics focuses on the different plate boundaries. The many different features seen at these boundaries provide overwhelming proof that the sea floor is indeed moving. In fact, it is being recycled. Evidence supporting plate tectonics include earthquakes and volcanoes, paleomagnetism, such as polar wandering and magnetic reversals and seafloor spreading, deep ocean drilling, and the presence of hotspots. Information on these topics can be found in your textbook on pages 521 to 527, and also in your text on pages 540 to 547. When we look at the evidence for plate tectonics, the first piece of evidence we'll look at is the location of earthquakes and volcanoes. Earthquakes and volcanoes do not occur randomly throughout the world, but occur in rather limited belts. These belts mark the location of plate boundaries. The largest active belt in the world surrounds the Pacific Ocean and is referred to as the Pacific Ring of Fire. So if we look at the diagram to the right, we can notice that surrounding the Pacific Ocean, we have a very dark band of dots. These dots indicate the presence of earthquakes and volcanoes surrounding the Pacific Ocean, and this is referred to as the Pacific Ring of Fire. 90% of all the world's earthquakes occur within this band. Some of the more famous volcanoes are found surrounding the Pacific Ocean, such as Mount Fuji in Japan, Mount Pinatubo in Indonesia, and several outlining the eastern portion of the Pacific Ocean. These boundaries are areas where compressional forces cause tectonic plates to move toward one another, and stress will build up within the rocks. When the stress is great, fractures, called faults, may occur within the tectonic plates, and the plates may suddenly slip, which result in an earthquake. The boundaries are also places of high heat flow, which are characterized by molten rock rising to the surface and forming volcanoes. Such volcanoes could be an example of Mount St. Helens in the United States. So, in summary, on the borders of all tectonic plates, we do see evidence of earthquake activity caused by compressional forces of tectonic plates building up stress, and volcanoes. As you see in the diagram to the right, we see the border of two tectonic plates, an ocean plate being subducted, and the resulting continental plate, which has volcanoes forming on a surface. So earthquakes and volcanoes provide evidence for a mobile Earth, and they are found bordering the continents and bordering each of the tectonic plates. The second piece of evidence, when we look at plate tectonic theory, focuses on paleomagnetism or fossil magnetism. Paleomagnetism is the permanent magnetism in the rocks which indicates the direction of the magnetic field when the iron-rich minerals became magnetized. The most persuasive piece of evidence to support the plate tectonic theory comes from the study of the Earth's magnetic field. The ideas of polar wandering and magnetic reversals on the ocean floor provide this evidence. Basaltic rocks contain iron-rich minerals, which become magnetized in the direction of the magnetic field at the time when the rock had solidified. If the rocks move, the magnetism in the rocks retain its original magnetic alignment, and they remember the location of the magnetic poles at that time. So as rocks move for millions of years, the magnetism in the rocks themselves do not change. When we look at paleomagnetism, one aspect of paleomagnetism is called polar wandering. Polar wandering is the apparent movement of the magnetic poles as outlined from studying the magnetism fossilized in successive basaltic lava flows ranging in age over millions of years. A plot of this magnetism showed that the magnetic poles appear to change position considerably over the past 500 million years. So if we look at the diagrams to the right, in the top diagram of the Earth, which shows the present location of the Earth's continents, we see that we have a green line outlining the apparent wandering of the polar position for North America, for Eurasia, and the red line shows the apparent wandering of the magnetic polarity for North America. So as the poles moved, or as the continents moved, at 100 million years ago, the apparent position of the North Pole, magnetic North Pole, would have changed. 300 million years ago, would have changed. But when we put these continents back into realignment as they were during Pangea, the actual polar wandering curves now tend to match up with one another. So at 100 million years ago, the magnetic North Pole was pretty close together. 200 million, 300 million, and 400 million years ago, the apparent position of the magnetic North Pole would be exactly the same position. So this idea of polar wandering provided evidence to support the idea of a mobile Earth and the movement of the tectonic plates. This was clear that either the magnetic pole had moved with time, or an idea known as polar wandering, or the basaltic lava flows on the ocean floor had moved with time, and this could be explained by continental drift. Thus, plate tectonic theory is believed to be the best explanation for polar wandering. If the magnetic poles remain stationary, then their apparent movement would have been caused by the drifting or the moving of the continents. A second example of paleomagnetism would be the magnetic reversals in the ocean floor as the sea floor was spreading. Paleomagnetism also provided evidence for plate tectonic theory when scientists discovered that the magnetic field reverses its polarity. Basaltic lavas, which contain iron-rich minerals, solidifying during a time of reverse polarity, would display the opposite magnetism as the rocks forming today, which has normal polarity. Rocks with magnetism as the same as our present magnetic field is said to have normal polarity, and rocks with the opposite polarity is said to have reverse polarity. So if you look at the diagram below, we see that the light areas represent normal polarity, and if we look directly above the magma chamber, where rocks are presently forming at ridges today, it is forming with a normal polarity, so they're light in color. As we move away from the ridge, we see corresponding red areas on both sides of the ridge. These red areas indicate reverse polarity. So if you look closely at the pattern that's preserved in the ocean floor as you move away from a mid-oceanic ridge, we will see a similar pattern of normal and reverse polarity, which are approximately the similar thicknesses as we move laterally away from a ridge. Thus, the pattern would be repeating the same on both sides. This alternating magnetic polarity can be seen in two areas. The alternating magnetic polarity can be seen in successive lava flows, which make up volcanoes on land, and they also can be seen in the basaltic rock making up the ocean floor. If you look to the diagram to the right, we see that a lava flow that comes out of a volcano basically will be preserved in the present magnetic field. So as millions of years pass, this magnetic field tends to reverse, and if we look at successive lava flows from lower in a volcano to upper areas of a volcano, we see a repeating pattern of reverse polarity, normal polarity, reverse polarity, and so on. So the magnetic reversals can be seen in alternating lava flows that make up composite cones in volcanoes. At the ocean ridges, the plates move apart and new basaltic rock is added to each plate. The magnetism of these basaltic rocks appear to alternate to produce identical magnetic patterns on both sides of the ocean ridges. This proved to be the strongest evidence to support seafloor spreading, and therefore supported plate tectonics. This alternating magnetic pattern between normal polarity and reverse polarity is seen in the diagram below. Normal polarity is indicated by light areas, and reverse polarity will be indicated by the pink areas. And if we note, the farther we move away from the ridge, which is directly above the magma here in the diagram, we see the same pattern of normal, reverse polarities on both sides of the ridge as we move farther away from the spreading center. So magnetic reversals in both the ocean floor and in volcanoes provided evidence to support the plate tectonic theory. The third piece of evidence that was used to support plate tectonic theory will be ocean drilling. From 1968 to 1983, the Deep Sea Drilling Project collected convincing evidence confirming the seafloor spreading idea, and hence evidence for the plate tectonic theory. Scientists studied drill core samples of the ocean floor, and sediments on the ocean floor were collected with increasing distance from ocean ridges. What scientists had found, the greater the distance you go from the ocean ridge, farther away from the ocean ridge, the older the igneous rock had gotten, and also the older and thicker the sediments that were produced. This was overwhelming evidence to suggest that the ocean floor is relatively young at mid-oceanic ridges and tends to get older the farther you move away from the mid-oceanic ridge, thus providing evidence that the rock is moving laterally from the mid-oceanic ridge. So therefore, evidence from ocean drilling would support the idea of plate tectonics. When the oldest sediment from each drill site was plotted against the distance from the ocean ridge, it was noted that the age of sediment increased with the increasing distance from the ridge. And this can be seen in the diagram to the right. If we look at magma rising up at the ridge, and then the successive layers of basaltic rock moving away from the ridge, we notice that the age tends to increase the farther we go away from the ridge. The diagram shows age of 0 years directly at the ridge. That's new rock that's freshly formed. Then the farther we move away, we get 0.7 million, 0.9 million, 1.05 million. So the age of the igneous rock, the basaltic rock that make up the ocean floor, increases in age the farther we move away from the oceanic ridges. This evidence also confirmed the idea that ocean basins are relatively young, because no sediment older than 180 million years was found, and continents were dated to be 4.6 billion years, which is 4,600 million years old. So ocean drilling provided overwhelming evidence to support the ideas behind plate tectonics. A fourth piece of evidence used to support plate tectonic theory will be the idea of hotspots. Hotspots were found while mapping the seafloor in the Pacific. It revealed a chain of volcanoes and seamounts that extended from the Hawaiian Islands to the Midway Islands, and they continue north to the Aleutian Trench off the coast of Alaska. Scientists proposed that a plume of magma presently exists beneath Hawaii in the middle of the Pacific Plate, and as the Pacific Plate moved over this stationary magma chamber, it created a series of new volcanic islands. This confirmed that the tectonic plates do move in relation to Earth's interior, thereby supporting the theory of plate tectonics. Radioactive age dates of the seamounts and the volcanic islands confirm that the age increases the farther you move away from Hawaii, and therefore the farther you move away from the hotspot. So if we look at the diagram below, we will see that Hawaii is located directly above the hotspot and is currently being fed by magma from this hotspot. And this is evident by the active volcanoes we see on the island of Hawaii, such as Kilauea. The farther we move away from Hawaii, such as Maui and Oahu and other volcanic islands stretching in a northeast pattern, we see that these islands are progressively getting smaller due to erosion and the sinking of the ocean floor, and also they are older in age, as determined by radioactive dates. So therefore, hotspots will be overwhelming evidence to support the ideas behind plate tectonics. Let's have a look at some examples from past public exams. First question reads, based on the information below, which is true of letters X and letter Y? If we look at the diagram to the right, we see letter X represents an area which is light in color, and area Y represents an area which is dark in color. These light and dark patterns on the ocean floor represent different magnetic polarities. Therefore, we notice that area X and area Y are different polarity, and also in relative position, area X is closer to the mid-oceanic ridge than area Y. Therefore, area Y, seen as farther away, must be older. So the answer that we're looking for is based on the information below, which is true of letters X and Y. X and Y are different in age because they are located at different positions from the mid-oceanic ridge, and they also represent different polarity because area X is light in color, whereas area Y is dark in color, and they represent opposite polarities. So the answer to the first question will be A. Area X and area Y are different in age, and they have different polarities. Question 2 reads, what do apparent polar wonder paths obtained by paleomagnetism tell us? The answer here, if we look at polar wonder paths, they basically outline the path of where the Earth's magnetic poles would have been in the geologic past. So over several hundred millions of years, they trace the actual position of the Earth's magnetic pole. And if the paths are different, this tells us that number one, the Earth's magnetic pole must have moved, or the rocks that we determine the magnetism from must have moved. And the more logical answer will be the continents would have moved. Therefore, the answer to this question will be D. The lithospheric plates have moved over time. Therefore, the apparent polar wonder paths would have changed over time. Example number 2. First question reads, which plate tectonic evidence is described in the information below? The information reads, as igneous rocks cool at mid-ocean ridges, the iron-rich minerals align to the Earth's magnetic poles. The alignment of iron-rich minerals to the Earth's present magnetic pole would give you an indication of paleomagnetism, the preservation of the magnetism in the rocks. So the answer to the first question would be C. Second question reads, what contributions to the reverse magnetic patterns found on the ocean floor near ridges? So reversing of magnetic patterns on the ocean floor would indicate that the Earth's magnetic field had changed with time. So the answer to this question would be C, alternating magnetic polarity of Earth's magnetic field. So in the past, you would see an alternating of the magnetic polarity of Earth's magnetic field. Presently, we are experiencing a normal polarity, which is a high polarity, and in the past, this polarity fluctuates from high to low, and low would represent a reverse polarity. Your turn. Take the time and complete an answer for the following question. The answer to this following question will be on the slides that follow. The question reads, with the aid of a labeled diagram, explain how hotspots can be used to support the theory of plate tectonics. So if we look at a diagram representing the movement of an oceanic plate above a hotspot beneath the ocean, we can see a series of volcanic islands represented by A, B, C, and D. The island that is presently over the hotspot is actually being fed by the magma and has an active volcano in that island. Islands B, C, and D are extinct volcanic islands that are progressively moving away from the hotspot as the plate moves over the hotspot. So to answer the question, the hotspot can prove the idea of plate tectonics because we know there are areas of hotspots in the Earth's interior. They burn their way through to the crust. If the crust didn't move, then there will be one very large shield cone above the hotspot. Instead, we see a chain of volcanic islands that are increasing in age as we move away from the hotspot. The differing ages show the direction that the plate is moving. It moves in a direction that the islands get older. So in the diagram here, and in the case of the Hawaiian island chain, we see that the hotspots are stationary and volcanic islands extend in a direction away from the current active volcano. So this is overwhelming proof that we have a mobile Earth, and it supports the ideas behind plate tectonics. So in summary, some of the evidence supporting the plate tectonic theory include the presence of earthquakes and volcanoes. Both earthquakes and volcanoes are located at the edges of plate boundaries for the most part, and they are caused by the movement along tectonic plates, where plates move apart and where plates collide. Number 2, paleomagnetism also provides evidence to support the plate tectonic theory. Here we look at two types of paleomagnetism. One, polar wandering, which preserves the Earth's magnetic field at the time the rock formed. And number 2, magnetic reversals, which suggest that the Earth's magnetism changes in intensity over the years, and this is preserved in the seafloor as the seafloor moves away from one another at ridges, which we call seafloor spreading. A third piece of evidence to support plate tectonics is deep ocean drilling. Deep ocean drilling away from a mid-oceanic ridge would support that the age of the seafloor, the farther you move away from a ridge, gets older. And a fourth piece of evidence to support plate tectonics is the idea behind hotspots. A hotspot is a stationary magma chamber located beneath the tectonic plate, and as the tectonic plate moves over the hotspot, new volcanoes yet fed by the magma coming from the hotspot. Therefore, you find a chain of volcanoes extending away from the active volcano that is directly above the present hotspot. So these four pieces of evidence provide overwhelming evidence to support the idea behind a mobile Earth, and therefore is direct evidence supporting the plate tectonic theory.